All right, this video is going to go over the derivatives of transforms theorem. So we do have a couple theorems from the section 7.3 in the book where if you had like e to as and you multiply that by f of t, that there's different things that you can do to move that along the s-axis, right? Here we're looking at like if I have a polynomial in front of a function, what can I do? And I want us to jump into this first example. So long ways, what we would have done with the full definition of a Laplace transform is you would have taken the integral from 0 to infinity of e to the negative st times t times sine of kt. And we'd have to do some kind of like big old mamma jamma like integration by parts that just seems ridiculous, like parts within parts. And so we want a different way. We want a different way in order to do this. And so let's go ahead and use this theorem here. In this case, n is equal to 1. And my f of t is sine of kt. So that way we're going to end up having just like a generic form of this. So t times sine to the kt, like what is the Laplace of that? All right, so it says that to find the Laplace, I'm going to take negative 1 to the n, and then I need to take the first derivative with respect to s of whatever f of s is. So the sine is k over s squared plus k squared. All right, well, I'm going to take the derivative. I'm going to have a negative 1 in the front. I'm going to take the derivative of this using quotient rule. So low d high minus high d low all over low squared. This piece here is going to give me 0, and then I'm going to end up having a negative and a negative there, so 2k times s over s squared plus k squared squared. All right, so let's go ahead and look at a problem here. So I have a second order differential equation. It kind of looks like the spring constants that we talked about before. So like with that spring constant here, maybe it starts initial position with initial velocity. So just like this might be a different way to solve that type of problem. And so let's go ahead and take the Laplace of x double prime and the Laplace of 16x. And then for cosine, we get s over s squared plus k squared. All right, so this is 0. I'm going to add 1 to this side, and then I'm going to factor out a big x, and I get s plus 16. And I'm going to go ahead and leave this as two separate fractions. And I'll show you why here in just a second. What I recognized is when I divide this over, I get a repeating piece here. And then I get just 1 here. So I don't want to, or I guess I should backtrack. What I want to say here is I want to always double check and see, like, if I make this the same fraction, am I actually making it any easier for myself? I'm going to end up getting something like s squared plus 16. I'm going to end up having to do partial fraction decomposition. And so sometimes it's easier just to leave it and see like, does this help me? And in this case, it does. This piece right here is a sine kt. And then if you notice from what we just did over here, this is a t sine of kt as my inverses. So little x of t must be, now remember I need a 2k up here, and in this case k equals 4. So I should have an 8 up here, but I don't. So I'm going to write this as 1/8 t sine of 4t plus, and then I should, for this, have a 4 up here, but I don't. So 1/4 sine of 4t, and that's my solution right there.